I am the only Italian speaker here, and I'm starting 1 minute after. So this is a very good reason for me not to follow the laws. Used to Italians just establishing rules and then just forgetting about the application of them. So, but I mean, it is going to be, I will try to respect the times, right? So, after the Jean-Michel presentation about the material science and the application of material science to the powder metallurgy world, now my presentation is focused onto a overall introduction of powder metallurgy. And the first thing that I can say is that you can refer to this leaflet, little book, which you have in your book of things. If you don't, just go and refer to the desktop, right? So theoretically, my presentation could finish here. Basically for two reasons, because it's an introduction and because you will see the majority of things again in the following presentation. But I am trying to just start with something which will capture your attention. I hope so, at least. Now, what is the use of powder metallurgy and what is the word of powder metallurgy? So just start with the www. That's to say the what, why, and when powder metallurgy is applied into the industrial world. And the first thing that we can say is that powder metallurgy can be defined. I will make some general definition, and then we will see that they are sort of Italian-like. You make definition, and then you find, you know, some different things. Let's say so. So, in general, we can define powder metallurgy as a materials forming technique, which is, let's say, starting from the point of, or the need of create powders, which can be metallic or non-metallic, and somehow powders need to be assembled to make an artifact of a desired shape. In general, we can say that these particles have to adhere one to the other. That is sort of valid. I will show you a couple of examples, especially in the field of soft magnetic compound, where this is not that valid. Usually, this kind of powders are put together and made adhere at high temperature by a process which is named sintering. Again, that is not valid 100% of times, but we will see the counter cases. And these particles, or the products which are coming out from the thermal process, may undergo for a further processing or for a finishing step, so to form the final compound. Here you see a couple of examples. This is very general. We will see that later on. And this is a set of diamond bites for cutting, to be used as cutting marbles. Now, what is PM in terms of numbers? Again, another reason for me to go extra time, right? What is the estimated or the global part production? Actually, you can see statistics, different types of statistics. You can refer to the EPMA website. There are also other websites, but let's just refer to that. And we can see that basically figures can be divided into hard metal production. In terms of, in terms of billion euro, the last figures of 2014 are about 15 billion euros, whereas for the structure PM is about 8 billion euro. Here is not taking into account the part related to additive manufacturing. We will see that later on. as for what concerns the amount of powder, you see here that we are in the range of 1,000 kilotons, which are roughly distributed into Europe, USA, another market, Asian market, let's say roughly 1/3 each. It's not that correct, but we will see that again later on. What is PM? What is PM? Once PM could be, let's say, double linked to the term of sintering, which is a process involved in the heat treatment of green powder compacts at elevated temperatures, defining elevated temperatures, anything which is above 0.5, the melting temperature expressed in Kelvin. By means of this heat treatment, a powder compact is densified and gets into the desired mechanical properties. Actually, this was valid for the majority of the cases when I was in the, a couple of years ago, in my first, when I was attending the summer school. Right now, is not that valid anymore. Well, no, it is still valid, but there are counter cases, as we will see later. What is the definition of sintering? If we go for the ISO definition, sintering is referred to as the thermal treatment of a powder or of a compact at a temperature below the melting point of the main constituent for the purpose of increasing its strength by bonding together the particles. So basically this is opening up a set of possibilities, a set of chances that will be well deepened in the sintering presentation, in the fundamentals of sintering, which will be held this afternoon by Professor Bernd Kibak. Now, we have sort of run for the what is PM. Now, why PM? Why do I have to use PM? I have to use PM because it is a highly developed method for manufacturing reliable ferrous and non-ferrous, or let's say metals and eventually not that so much metals, according to the type of definition that you apply to metals. But again, this is another thing. It provides a flexible range of processes and materials. Of course, according to the different techniques which are related to powder metallurgy, you can go for a quite large variety of shapes and sizes that can be obtained. It is generally associated to cost savings, and we will see in the next slide what this is meaning. And of course, the combination of the former provides quite a good reason for that. Now, what are the basic points which are related to PM? What kind of reason? Well, actually, you will see in whichever kind of text that you go for any kind of deepening, that PM, it is always referred to as eliminating or minimizing the machining. It eliminating or minimizing the scrap losses. And this is quite a good reason. I mean, this would be already a good reason to just invest a lot in PM. Of course, this is not the only one. It is providing also good surface finishing. Well, that is depending on the type of technique. You will see within this course that different kind of processes related to the production of PM are creating or are resulting in different surface finishing. But in general, we can see that they are quite good if compared to other producing processes. It provides materials which can be heat treated, but one of the peculiarity of PM, it is that it is providing controlled porosity. Well, porosity may be an issue, may be a problem, especially if we do take into account the mechanical properties, as you will see later on. But at the same time, the fact of having a controlled degree of porosity may be absolutely fundamental for some application. And we will see a couple of examples that would not be possible to be produced without the use of PM. Then manufacturing of complex or unique shapes, high volume component production. Actually, that is valid for the majority of cases, but at the end, it is cost effective. Now, if we just make a comparison between PM and other processing techniques, one point which is coming out is that the degree of raw material utilization is huge, is tremendously higher than what can be deriving, for example, from other processes like machining or like eventually casting. Well, casting, they are comparable. It depends on which kind of casting you apply, which kind of alloy you apply. But I mean, if we go for the raw material utilization, the sintering process is going, or the PM process in general is going to levels which are around 95%. And at the same time, it is providing, for the majority of cases, the lowest energy requirement per kilogram of finished part. Now, these are, again, good reason to go for PM, but we have the last W. That's to say, when we can use PM. Actually, there are different occasions or different cases when PM can be used or should be used. The first one is when let's put it this way. We can use PM and have very high cost savings if compared to other production processes. And this is valid when we have to produce large manufacturing lots, complex shapes, small size parts. This is in general associated to a no improvement in mechanical properties of a given compound. That's to say, if we compare the mechanical properties of the PM produced part and of another technique of production, we don't have improvement in properties. Then there is another point when to use PM. That's to say, when we do have a high properties to performance rate. Usually, in this case, we have higher properties than any alternative manufacturing process. And last but not least, when PM is the unique way to manufacture. What is the mean of unique? Can be both in terms of manufacturing process or in terms of design process, as you will see tomorrow. Yep, in the additive manufacturing. I will just provide a couple of examples. Now, according to the subdivision that I was making, when PM can be used, first field of application. Application for automotive. You see here a set of samples that you can easily find in the EPMA website. What is that? Why do I have to use them? Well, actually, this is a rough table that you can find in the Design for PM course, where you see here the set of action that you are following in order to produce that kind of component, that is connecting rod or whatever it is. The energy expressed in kilowatt hour per piece is 1.243. What does it mean? Who knows? At the moment, it is not that important. Just go for the equivalent in terms of energy, which is spent if instead of producing that kind of component with that kind of composition, just notice this, finished part weight, 312 grams, used weight, 328 grams. You lose not so much. Using a more traditional process by forging and machining, we have a set of action. We start from something which is about 500 and something grams for ending at the same weight. That's to say, the weight loss is 200 and something grams. But in terms of energy, here we have 2.847. That's to say, by comparing the two processes, what we have is a process here which is, in terms of energy, consuming 43% of the more, again, traditional one. Now, this is already a good reason. Or this is already a good set of examples just to divert to PM. Of course, it is not the only one. I was just introducing you the fact that PM can be used when an improvement of powder can be or is needed. Let's see the example of what is happening for tool steels. Here we have a very rough microstructure of what is coming out for a conventional ingot by casting. If that kind of ingot is deformed, and I was just taking out the hot working, we have a distribution of carbides, which of course is elongating in the direction of working. What is happening for powder metallurgy? Well, actually, the product appears to be more homogeneous, with a better distribution, for example, of carbides. What is this resulting? Well, in terms of mechanical properties, everything is referred to mechanical properties. Who cares about these mechanical properties? Yeah, they are important, unfortunately. We are engineers, so we have to remember that they are important, somehow. So, what is this? Well, actually, we can refer to a carbide like a sort of defect. How are they distributed? Well, they are distributed in a way which is somehow more homogeneous, more regular. What is this resulting into? An improvement, of course, a potential reduction of elongation at rupture, but a much higher tensile strength, or in general fracture strength of the component. Again, tool steel, another application, another example, cemented carbide. What is a cemented carbide used for? You will see again tomorrow, quite a full day tomorrow. A set of application of and use of cemented carbides. Just in a little pillow. Cemented carbide is something which is made by, in general, tungsten carbide plus cobalt. And cobalt is a sort of glue which is keeping together all the other part. This is very, very short. How could you take that, or how could you make that together, staying together, providing all the properties that are so important, at least in terms of the market, as I have shown you in the one of the first graph. That kind of cobalt is acting like a glue, and it is providing this type of microstructure. And this is only possible if you go and if you use powder metallurgy. Again, another set of application. Let's go for another product or another set of products. How can you produce, for example, a filter, or for example, a bearing, which is self-lubricate? You will see again some examples of that. How can you produce that in another technique? Well, actually, you can start with a massive product and then drill a lot of holes. That could be an option. I mean, at least that is what a student of mine was telling to me in an exam. He was not that successful in passing the exam, but that is another thing. So here you can use the porosity not as a negative part, but as the main characteristic of the component. Like, for example, for filters, that is clear. For self-lubricating bearing, we have a porosity, we put something inside, whichever is oil, for example, and then we have something which is under stress, just helping the system to improve the mechanical behavior. Again, you will see that. Another type of case which is simple or which is used for PM is the application of the so-called FAST technique, field-assisted sintering technique, or also fast, rapid. What is the meaning of rapid? Well, actually, there are a set of different patents on that. I will come back on this. But when we are speaking about fast, we are speaking about something which is in the range between minutes and not hours. And that can be in the range of 15 to 30, 45 minutes for the entire process, or in the range of about 1 minute for the entire process from compaction to the as sintered product. Of course, in this case, the concept of sintering is slightly different. It is not something which is or which can be described in the definition that was given to you earlier on. And then this, additive manufacturing. So I have spoken, I have spoken for a while, so this is a short video. Unfortunately, no sound on that. So additive manufacturing is something which can be used for the production of a turbine, as the example was giving. What is that resulting into? You start from a drawing which is sliced. That slicing is put into a machine governed by the software. You load the powder into tanks. And then what is happening? You have the charging of the powder, preheating, and then the electron beam, which is acting on the powders in order for them to locally melt and provide a compact which is having quite peculiar properties. Of course, this is just an introduction movie. You will see this quite deep into details tomorrow. Now, you have the production of the component. You see that here, oops, sorry, just step back. The component is growing from the top to the bottom. It is moving down. Then what is happening? When you finished the original file, that kind of job is taken out from the machine. And the component is set to an area where you recover the powder or the loose powder, okay, let's see if it is working here, yeah, okay. And then the final component is being produced. Which are the peculiarities of this? I just ask for 5 minutes, 10 minutes of patience. What is the industrial history of PM? When PM was started, it's a relatively young set of processes, but we can see here a development, at least under the industrial point of view, which is starting from the late 19th century with the development of technique for the tungsten filament production. Then in the 20s, the first production of hard metals and self-lubricating bearings. In the 40s, or anything from the 20s and the 40s, the production of structural parts, then metal injection molding components, and around 20 years later, the fast techniques and the additive manufacturing. If we go for additive manufacturing, which is just the last big development of powder metallurgy. Just to give you numbers. This presentation 5 years ago would not have taken almost into account the set of additive manufacturing. Right now is covering additive manufacturing. Yeah, you see here from 1985, foundation of EOS. No, sorry, a bit later, 1989. Then we have today production of by GE of the turbines. Production of powder for additive manufacturing. Just to give you numbers, Lionel, please help me. How many papers in additive manufacturing were we discussing in Milan? About 50% of the overall number of papers of the conference.
We have at least one session every day, every morning, every afternoon. So there is additive manufacturing on the 4 days of the event. When for some other sector, we have just half a day.
Yeah. So basically, you can see that. I mean, about 50%, roughly, I may be wrong, are focused on additive manufacturing, powders, processes, post-treatment, whatever. 5 years ago, the amount of papers on additive manufacturing was like 1%, 2%, something like that. So here is, as Lionel was focusing before, was introducing before, powder metallurgy is something which is every day, every year opening up new sectors, new areas. Now, back to the presentation. What kind of processes can be, let's say, found in the overall world of powder metallurgy? The conventional press and sinter, which is just using, I would say, the majority. Dimitris will tell us something about the powders later on. I think that traditional press and sinter is using the majority of the powder. Then powder injection molding, the hot or the cold isostatic pressing, other shaping methods like powder rolling or something like that. Then the field-assisted sintering techniques, and of course the additive manufacturing. Now, what in terms of comparison, like powder production and complexity of the components? Can we just characterize the entire world of PM in a plot like that? No. Why? Because according to the fact that we are using press and sinter, we are using metal injection molding, or we are using rapid prototyping, somehow additive manufacturing, even if this is not that correct, we are locating in different areas of the graph in terms of complexity of components and in terms of powder production. Generally, for PM and metal injection molding, we are at the extreme, but with a high production rate. Whereas for additive, we can be ranging from very simple, not that convenient, or very complex component, but with a number of production which is limited, at least if you don't buy plenty of additive manufacturing machine. Now, do you know the meaning of ASAP? I think you do. No, you don't. This is the most difficult part because, I mean, already here in the first 30 minutes of my presentation, I'm quite on schedule. No, I'm 5 minutes late. Who cares? The point is a overall introduction. Right now, it's a bit more different and more difficult to me because you will see, starting from the next presentation, no, next presentation is coffee break. Starting from the second presentation, what is the common point, which is eventually the only common point that is linking all the different kind of processes. That's to say, we have to start from powders. Luckily, I've just shown you that sintering is not so common to all the systems. Some systems do not use thermal sintering, but at least we have to start from powders. Now, which kind of methods do we have to produce these powders? It depends. On what? On the process and on the type of powder that you have to produce. Basically, there are chemical methods or physical methods like atomization, mechanical methods like crushing or millings or mechanical alloying in terms of the physical, in terms of the chemical, solid state reduction, electrolysis, reaction with gases, and hydrogen reduction. Of course, every different method is providing a different type of product in terms of the powder, which is to be used in a different process, as you will see later on. What about press and sinter? Press and sinter used to be or is the traditional way of referring to powder metallurgy. It has a cycle starting from the powder mixing, different powder mixing. Of course, there are powders that can be already admixed or not. Dimitris will show you a lot about this later on. Forming, thermal sintering, which can be followed by a repressing and eventually a resintering, and eventually you can end up with your finished product like that. Of course, you can adopt plenty of differences, plenty of turns in the process according to the type of final property that you need or that you want to have in your finished product. Press and sinter is pressing and sintering. Jean-Michel before was already explaining you about this plot. That is related to the fact that some mechanical deformation is appearing in the system, and he was already explaining you the reason why. By this kind of method, it is impossible to get the total densification of the component. But that is the first part. Then the second part of the process is end sinter, which are the typical temperature for sintering. Again, it depends on the type of powder that you are using. Here you just can find very rough values, which are ranging from 500 and something for aluminum up to 1000, 1200 or 1300 if you go using steel powders. Then, of course, you will see that according to the temperature of sintering and to the time of sintering, your final structure will change. What about the sintering? Well, this is sort of nightmare for whichever kind of student approaching material science. That's to say Ellingham. Well, do I have to say anything more about Ellingham? No. I mean, it's our problem, our common problem, right? Somebody else will, I think, you have already known, will spend this presentation on this, and on the importance of Ellingham. What I can tell you that, I mean, steels, or in general powders, the majority of powders, tend to have a little bit of problem when they are treated at high temperature. So you have to be careful on that. But Christian will be much more precise than I am. Now, what can happen during the sintering? New components may be formed. Actually, there can be some diffusion happening. There can be also some liquid phase forming. If you go back to the definition that I was providing before, it's the ISO temperature below the main constituent melting temperature. It doesn't mean that it's tricky. It doesn't mean that nothing can go on melting. And this is something, as you will see again tomorrow, which is quite important for the definition of some properties of sintering materials. Now, another thing. I'm sorry I have to run a bit. I cannot focus on that. But again, all what I'm doing here will be deepened by other people's presentation. Metal injection molding. You take what plastics did, use your powder as a filling phase, and you find metal injection molding. I'm not a big fan of plastics, and this can easily be seen. But I mean, I'm recorded, so I cannot go further in my comments on plastic material. So this eventually, Lionel, please cut this part, right? If you want to promote this to plastic people. Anyway, what is the point of metal injection molding? You go and just admix the metal powder or the ceramic powder with a set of binders, just admix them, then you create pellets, that is to say something which is looking like a small Lego object, Lego brick. You put that into an injection molding press, inject it, get your final component which needs to get rid of the plastic part by the so-called debinding step, and then you go for sintering and you get the final part. What is the basic main difference between press and sinter and metal injection molding? The fact that here you use a higher amount of binder, which of course needs to be eliminated. So the point, what is the point here? Press and sinter is something which is just characterized by a small, when it is present, a small reduction into the components part, whereas metal injection molding is usually referred to a medium to high reduction in the dimension of the component. You will see again a presentation about metal injection molding by Frank Petzel tomorrow or the day after tomorrow. Another process which is quite relevant is the isostatic pressing. Might that be cold isostatic or hot isostatic? What is the difference? In one case you work at medium to low temperature, in other case you use hot temperature. And then of course hot temperature is depending on which is the type of alloy that you are generating. What can you produce by means of hot isostatic pressing? You see here one of the components which was winning the award at the EPMA competition in Hamburg. Just see the dimension. It is not as the typical type of metal injection molding component. Metal injection molding, you will see, it is something which is used for production of components which are like about a gram, something which can easily go into the mobile phone. Well, this is quite a high or quite big mobile phone. It can eventually be a satellite phone or a Martian phone. Now, one point is that I've introduced you earlier on is the fact that by means of powder metallurgy, you usually save. What do you save? Money, powder, or whatsoever. Here, just see what is the demo case, which is that component production here with the traditional type of production starting from an ingot which is weighing 700 kilos, ending up at the end a component which is weighing 90 kilos, right? So this is the traditional set. Percentage of raw material usage, 13. What is coming out by the hot isostatic pressing? You start with 120 kilos, you end up with 90 kilos, percent of raw material use, 75. Total energy consumption, 155.500 megajoule, 27. Total carbon dioxide equivalent, 10.5 versus 2.0. It is not only something related to properties, also in the case of isostatic pressing, but in the case of more effective production. Not only that. What can you get but hot isostatic pressing? A set of components, like what you see here, cutting tools, hard metals, cermets, diamond tools, and also others. Now, another type of production is powder rolling. That is going to the alternative shaping methods. Very easy. You get a feeder, powder, and then you have rolls, which are rotating, and then what comes out from the roll is a pressed powder strip, which can directly go to the furnace, the sinter, for getting your finished strip or your finished product or elongating product. Now, something back to the fast techniques. Let me show you the video. Powder loading. That is sintered. So let's count it. 43.01. $43.19, 18 seconds. How is that possible? Well, you apply a pressure on punches, which are electrodes, and this is done into a graphite mold. At the same time, you apply a current, and that is resulting into the production of your final component by means of relatively high current, in the order of amperes, with a difference of potential which is volt or kilovolt. Why do I have to use this? Or what is the result? You see some sources that I was using for that. What is the result of doing that? Why do I have to use this kind of process? That would be fantastic. No, there are limitations, a lot of limitations, especially in terms of the maximum sizes and the complexity of the component that you get. You can get small components and you can get very easy shapes. But what is the best use for that? That due to the very high process cycle time, so it is short, you can mix up components. Here you see, for example, combination of precious alloys and gold and diamonds, which are treated together in order to get a very hard precious metals. This is something that I will come back later on as for application. That's to say, this kind of technique is allowing the combination of very, very different materials altogether, and the processing times are so short that it is not an issue to apply all the considerations that are used or that are to be applied when the thermal process is used. Now, one part or another important process, in addition to the traditional laser sintering or to the traditional electron beam melting that I was showing you earlier on, and that I will deepen in a little while, is the process which has been patented by Höganäs in terms of the digital metal, under the name of digital metal, and it is nothing but a print. You have a powder bed, and the powder is being delivered by a powder delivery system, and then you print, as if you were printing ink, some super duper secret component which is gluing the powder together. I'm making it very simple, right? But this is just for the sake of introduction reason and for the sake of the time. So you start from a file, which is of course slicing your component, then you print it, then you go to the traditional way of sintering, or sort of slightly modified way of sintering, as we can see in the video. So, powder printing or component printing, then elimination of the printed part, and then the post-treatment, which is using also which is ending up then in the sintering, right? Surface treatment, cleaning, and whatsoever. And that is one type of additive manufacturing. That is properly the 3D printing. Whereas the other types of additive manufacturing that are used normally can be divided into two big families. Actually, there is a point which is quite negative at the moment. That is to say, a lack of proper terminology. What does it mean? It means that the process, or better, the technology is quite new, so there is still the need of using or agreeing on the proper names to be put for whichever kind of technique. One point of characterizing or subdividing the additive manufacturing is by means of the what is proposed in this table, that is to say, directed energy deposition, acronym DED, or the powder bed fusion, which is the PBF. You see here that under this category there are a quite large set of different technologies that can be used, and several different companies which of course have developed their own patent. I show it to myself. First part, additive manufacturing using the powder bed. How can it be described? It can be described as a thermal energy which is selectively going and fusing regions of a powder bed. This is, using several different process names which are corresponding to a lot of different companies which I was saying you before have developed their own patent. You have seen here, or you can see here, the model of the EBM machine, which is nothing but what you have seen earlier on with the video. And this is a draft of the scheme for a selective laser melting process that you will see tomorrow. The material can be, or in this case, the material is always powder. When we go for what before was referred to a DED, we can use either powder or wire. In this case, we can describe the system as a focused thermal energy, which is used to fuse the material by melting as the material is deposited. You can see here that the approach is different. This is reflecting into different process names which are corresponding to what were the patent developed by different types of companies. Now, plenty of possible processes which are differentiating by small things, but what is in terms of the mechanical property that you can get on a given product? This is something which is derived by literature analysis. So here we have titanium, a general titanium alloy, the same one for the entire studies. Here we have the wrought, cast, let's forget that for a while, EBM, DED, DMLS. By using different processes on the same material, on a very similar material, we can go from an elongation of about 15% with a tensile strength of 800 to an elongation of 8 to something which is 50%, at least 50% higher in terms of the mechanical properties. Then, who cares about elongation? We go for this. Perfect. So, we start, we get this fantastic process which is additive manufacturing. We take the drawing as tomorrow it will be shown, put it into the machine, press a button, and that's it. Is it like that? No, absolutely not. Why? Because plenty of things have to be controlled, have to be, let's say, properly designed, since this is something that is totally different from what is the traditional processes, and it is also partially different from what is a traditional powder metallurgy process is. Why? Because in this case, we are creating something which is first melting. In which way? Layer by layer, or let's say couple of layers every time. And what is this resulting into? A microstructure which is totally different from what you can get from the traditional metallurgy, but also from what you can get from the powder metallurgy. So the point here is we start from powder and we get something into which we have to rediscover, or we have to reinvestigate from the very beginning, or sort of. Of course, there are plenty of works, plenty of researches doing in that field. Never do that again. No, I will not make any kind of other presentation, so be safe. Just two things. Here, which is the type of saving that you can get? Simple application. 55% of reduction in a component, saving $3 million into a life of an aircraft. Start to be quite appealing. Then, what? Creating or using additive manufacturing for something which is a niche of a niche of a niche of a market, jewelry. But that is quite promising. Let's see some, 1 minute. You will have to blame me for reducing your coffee break. Number of items produced by means of additive manufacturing, 1214, 1215, 1216, 14, 1217, almost 5 million. Growing and growing and growing. In terms of the market opportunities of 3D printed PM jewelry. Just see the revenue, which is ranging from 0 to 1 million in 3 years. And what is the outcomes, or what is the possible evolution of the market? Well, actually, in terms of strange alloys, peculiar properties, most of all, strange design, which is one of the most interesting part of the precious metals or the fashion world. Now, that is over. Thanks for your attention, and